Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is time-variant sinusoidal waveforms including phase shift. Our objective is to define phase shift and learn to evaluate time-variant sinusoidal waveforms including positive or negative angular phase shift. This lecture is predicated on the assumption the viewer has watched the sine waves, amplitude and effective values, and period and frequency lectures, all available at the Big Bad Tech channel. If you haven't watched these lectures yet or only dimly recall their contents, please take the time to do so now. This lecture presumes the viewer is familiar with radians, degrees, and conversion between these positional measurements, has more than a passing familiarity with a sine function, and can calculate peak, peak-to-peak, and effective magnitudes, as well as calculate period and frequency and evaluate a time-variant sinusoidal function. Thus far, we've been operating under the libertarian presumption that all sine waves are created equal. However, this isn't always the case. Sine waves, quite like your peers, are often given head starts or held back for various reasons, and as a result, this positive or negative shift can influence their behavior in the present. If you recall, one can describe a time-variant sinusoidal function using properties like peak value and frequency. Assuming this time-variant sinusoidal function represents output voltage, one can use the general expression of V of t equals voltage peak times the sine of 360 times the frequency times the time of interest, where the values inside the parentheses simply convert time of interest into an angle value usable by the sine function. This general format does not include a phase shift and assumes the sine wave initiates operation at 0 degrees. Recall that the circular origin of the sine wave assumes the far right side is the starting point for circular travel in a counterclockwise direction. Including a phase shift simply assumes our travel does not initiate at the origin, but rather at some other angular position in advance or behind the origin. A positive phase shift is simply the addition of this angular differential to the terms inside the parentheses and shifts our analysis counterclockwise by that amount. A negative phase shift, in contrast, is simply subtraction of this angular differential to the terms inside the parentheses and shifts our analysis clockwise by that amount. Including phase shift in the general expression, we simply add or subtract the phase shift to the terms inside the parentheses. For example, consider a time-variant sinusoidal with a 100-volt peak, a period of 15 milliseconds, and it happens to get a positive 30-degree head start to the day. This period corresponds to a frequency of 1 over 15 milliseconds, or approximately 66.7 Hz. The time-variant voltage expression will resolve itself into V of t equals 100 volts times sine of 360 times 66.7 times the time of interest plus 30 degrees. It makes sense that a time-variant sine wave with a positive 30-degree head start initiates at time t equals 0 with a value of 100 volts times the sine of 30, or 0.5 times 100, or 50 volts. Additionally, it makes sense that if this time-variant waveform underwent a full oscillation over a period of 15 milliseconds, it would also end at 50 volts. Sine waves, like circles, start where they end and end where they start. If we were to overlay a full cycle of a waveform with a positive 30-degree phase shift, with one with the same amplitude and frequency without a phase shift, you'll note that absolutely nothing has changed about the nature of the sine wave, only it's been shifted, hence the phrase phase shift, positive 30 degrees in advance, to the left or forward. The positive 30-degree head start essentially means the sine wave gets up 30 degrees earlier to start the day. You might want to pause the lecture and stare at this graph for a little bit to get the feel of what a positive phase shift implies. Note the x-axis isn't reflective of angular position, but rather time. Moving on. Using the time-variant expression accounting for phase shift, one can calculate output voltage magnitude at specific times. For example, at 2.4 milliseconds, one would substitute 2.4 milliseconds into our expression to arrive at 100 volts times the sine of 57.6 degrees plus 30 degrees, or 100 volts times the sine of 87.6 degrees, meaning that at a time ordinarily corresponding to 57.6 degrees, this function has a value equivalent to a normal sine wave 30 degrees in advance at 87.6 degrees, ordinarily just shy of the peak value. As can be expected, this results in an output voltage just shy of peak at approximately 99.9 volts. Similarly, at 4 milliseconds, it could be demonstrated the output voltage would be equal to 80.9 volts. Finally, at 8 milliseconds, it could be demonstrated the output voltage would be equal to approximately negative 66.9 volts. One could perform this analysis for an increasing number of points and arrive at the same conclusion we observed earlier. Nothing has changed, only the waveform has been shifted positive 30 degrees to the left or forward in time. Given we can convert between degrees and time, you'll note the positive 30-degree phase shift can also be measured in units of time. Given the sine wave has a period of 15 milliseconds, one can perform a unit conversion to find that a 30-degree phase shift is roughly equivalent to 1.25 milliseconds, meaning its zero crossing going positive is 1.25 milliseconds in advance, or in front of our start time. Let's now examine the consequences of negative phase shift. If a positive phase shift is to be likened to showing up ahead of time, a negative phase shift is quite obviously the opposite, being consistently late and behind the times. Does this remind you of a certain lab partner? A negative phase shift is simply the subtraction of that phase shift amount, thus retarding or slowing the sine wave start by this amount. Consider a time-variant sinusoidal voltage waveform with an 80-volt peak value, a period of 10 milliseconds, and it happens to be delayed by negative 15 degrees, whether because its car didn't start, or because it was too hungover, or some other equally lame excuse. Regardless, the zero crossing going positive that traditionally characterized the start of a sine wave simply shows up slightly late. A 10 millisecond period corresponds to a frequency of 100 Hz. The time-variant expression resolves itself into V of t equals 80 volts times the sine of 360 times 100 times the time of interest minus 15 degrees. As previously, it makes sense that a time-variant sine wave with a negative 15-degree delay initiates time at t equals 0 with a value of 80 volts times the sine of negative 15 degrees, or 80 volts times negative 0.2588, or negative 20.7 volts. Additionally, it makes sense that if this time-variant voltage waveform underwent a full oscillation over a period of 10 milliseconds, it would also end at negative 20.7 volts. Sine waves, like circles, start where they end and end where they start. As previously, if we were to overlay a cycle of a waveform with a negative 15-degree phase shift with one with the same amplitude and frequency, including no phase shift, you note that absolutely nothing has changed about the nature of the sinusoidal function, only it's been shifted, hence the phrase phase shift, negative 15 to the right or behind. The negative 15-degree delay means the sine wave stays in bed an extra 15 degrees and its zero crossing going positive occurs 15 degrees later than you'd expect. You might want to pause the lecture and stare at this graph for a little bit to get the feel of what a negative phase shift implies. Again, given we can convert between degrees and time, you'll note that the negative 15-degree phase shift can also be measured in units of time. Given the sine wave with a period of 10 milliseconds, one could perform a unit conversion to find that negative 15-degree phase shift is roughly equivalent to 416.7 microseconds, meaning its zero crossing going positive is 416.7 microseconds, or roughly 0.4 milliseconds behind or delayed with respect to our start time of the analysis. Using the expression accounting for phase shift, one can also calculate output voltage magnitude at specific times as we did previously. For example, at 2 milliseconds, one would substitute 2 milliseconds into our expression to arrive at 80 volts times the sine of 360 times 100 times 2 milliseconds minus 15 degrees, or 80 volts times the sine of 72 minus 15 degrees, or 80 volts sine 57 degrees, meaning that at a time ordinarily corresponding to 72 degrees, this sine wave has a value equivalent to a normal sine wave at only 57 degrees. As can be expected, this results in output voltage of 80 volts times 0.8387, or approximately 61.7 volts. Similarly, at 6 milliseconds, it can be demonstrated the output voltage would be approximately equal to negative 28.7 volts. One could perform this analysis for an increasing number of points and arrive at the same conclusion we observed earlier. Really, nothing has changed, only the sine wave has been shifted negative 15 degrees to the right. Let's try some illustrated example problems. Put your understanding of time-variant sinusoidal functions incorporating phase shifts to the test by solving for the desired quantities. In addition to solving for the desired quantities, see if you can draw a rough sketch of what these time-variant sinusoidal functions incorporating phase shifts look like on a graph. Keep in mind, I'm not asking for numerically precise graphs, but rather a quick sketch of what that particular phase shift implies. Note in example problem 3, I've drawn the waveform for you and expect you to root out the details. Pay attention as I've hidden some traps in this particular example set. It should go without stating that you can differentiate between properties like peak, peak-to-peak, effective, or RMS values in period and frequency. By all means, pause the lecture and give this your best shot. If you're tracking, you should have arrived at the following results. The first waveform has a peak value of 325.3 volts, a period of 20 milliseconds, and a phase shift of positive 10 degrees, meaning it'll be shifted 10 degrees to the left or in advance. A period of 20 milliseconds corresponds to a frequency of 50 Hz. The general expression results in V of t being equal to 325.3 volts times the sine of 360 times 50 times the time of interest plus 10 degrees. Substituting 3 milliseconds into our expression results in an output voltage of approximately 292.4 volts, as this illustrated operation shows. When we draw a rough sketch of this waveform with respect to time, you'll note the waveform completes a full oscillation over a period of 20 milliseconds. However, its zero crossing going positive is shifted positive 10 degrees, or 555.6 microseconds forward or to the left. Note that the time value corresponding to a positive 10 degree phase shift is arrived at by a unit conversion, as this illustrated operation shows. The second waveform has an RMS, or effective value, of 120 volts, a frequency of 60 Hz, and a negative 20 degree phase shift. An effective value of 120 volts corresponds to a peak value of approximately 169.7 volts. Hopefully you did fall into this trap. Peak value is always greater than RMS. A frequency of 60 Hz corresponds to a period of approximately 16.7 milliseconds. A phase shift of negative 20 degrees means it'll be shifted 20 degrees to the right or behind. The general expression results in V of t being equal to 169.7 volts times the sine of 360 times 60 times the time of interest minus 20 degrees. Substituting 4 milliseconds into our expression results in an output voltage of approximately 155.5 volts, as this illustrated operation shows. When we draw a rough sketch of this waveform with respect to time, you'll note the waveform completes a full oscillation over a period of 16.7 milliseconds. However, its zero crossing going positive is shifted negative 20 degrees, or 925.9 microseconds, backward or to the right. Note the time value corresponding to a negative 20 degree phase shift is arrived at by a unit conversion, as this illustrated operation shows. The third example problem is the same song in reverse. Here we're given a picture and being asked to solve for a particular value. It looks like it's got a peak-to-peak value of 400 volts, has a period of 12 milliseconds, and its zero crossing going positive is shifted to the left or forward by 1 millisecond. It looks like we've got to do some conversions. A peak-to-peak value of 400 volts corresponds to a peak value of half that, or 200 volts. A period of 12 milliseconds corresponds to a frequency of approximately 83.3 Hz. And a shift of 1 millisecond, given a 12 millisecond period, corresponds to a phase shift of positive 30 degrees, as this illustrated operation shows. Again, it's just a unit conversion, folks. Don't freak out. Don't make this too hard. If the whole waveform completes a 360 degree cycle in 12 milliseconds, it makes sense that 1 millisecond to the left is 1/12 of 360, or a positive 30 degree phase shift. The general expression results in V of t being equal to 200 volts times sine of 360 times 83.3 times the time of interest plus 30 degrees. Substituting 1.5 milliseconds into our expression results in an output voltage of approximately 193.2 volts, as this illustrated operation shows. Hopefully this set of illustrated example problems went smoothly. If it didn't, by all means rewind and revisit the explanation again and take another shot. Moving on. Phase shifting, as implied by its title, simply shifts or slides a waveform left or right and doesn't change its amplitude, period, or frequency. However, values at specific times will reflect this phase shift. When two or more waveforms incorporating phase shifts, one can establish a relationship between the waveforms. Importantly, the waveforms must necessarily have the same frequency. Consider waveform V1 of t, characterized by the following expression: 150 volts times the sine of 360 times 40 times the time of interest, plus a phase shift of 0 degrees. V1 of t has a peak value of 150 volts, a frequency of 40 Hz, a period of 1 over 40, or 25 milliseconds, and a phase shift of 0 degrees, meaning it's not phase shifted and its zero crossing going positive occurs at 0 degrees or 0 milliseconds. Consider another waveform in yellow, V2 of t, characterized by the following expression: V2 of t equals 150 volts times the sine of 360 times 40 times the time of interest plus 35 degrees. V2 of t also has a peak value of 150 volts, a frequency of 40 Hz, and a period of 25 milliseconds. The only thing that differentiates V2 from V1 is that it has a positive 35 degree phase shift, meaning that it's shifted positive 35 degrees in advance. Positive 35 degrees inside a 25 millisecond period corresponds to a leftward time shift of roughly 2.4 milliseconds, as this operation chain illustrates. Again, it's a unit conversion. Don't make this hard. When both these waveforms are placed in the same graph, there is an obvious relationship between the two waveforms, that of relativity. Relativity, as the name implies, relates two quantities with one another, and importantly, implies that one of the pair is used as a frame of reference from which the other is measured. With reference to your lab partner, you are an attractive, intelligent, and desirable individual. This relativity is also double-edged in nature. With reference to me, let's be honest, you look and smell like one of those grotesquely inbred boss-level characters in a bass fishing video game, and that's being polite. Given V1 and V2 are in all aspects other than phase shift identical to one another, it is immediately evident that V2 zero crossing going positive is 35 degrees in front of V1 zero crossing going positive, and V2 can be said to lead V1 by 35 degrees. Conversely, given V1 zero crossing going positive is 35 degrees behind V2 zero crossing going positive, it can also be said that V1 lags V2 by 35 degrees. Both statements, V2 leads V1 by 35 degrees and V1 lags V2 by 35 degrees, are simultaneously true, being merely different ways of saying the same thing.